Hi, my name is Michael Pendazis, and this is Math 231 Linear Algebra Online Lesson number 10. We're going to finish Chapter 5 and do Chapter 6. Okay, so the next section is 5.3, and it's on complex vector spaces. Okay, so first off, if we have a complex number named z and equals a plus bi, okay, so we're given that this is z, which equals a plus bi, is a complex number, then the following are true. The real of z, the real component of z is a, that little a there, and the imaginary component of z is little b, right there. Okay, so this is the real component of a and real component of z, and this is the imaginary component of z. Okay, so a is the real component of z and b is the imaginary component of z for this z equals a plus bi. Okay, the modulus of z is equal to the square root of a squared plus b squared. Okay, or you could say this is the absolute value of z. Okay, it has little names also. Okay, so you could say that's the absolute value of z. Z bar is equal to a minus bi. That's the complex conjugate of z. So that is the complex conjugate of z. Okay, and then z bar is equal to the modulus of z squared, which is a squared plus b squared. Okay, we would say, let's say we call phi is the argument of z. Okay, so if you draw a picture of z, what z is in the xy plane, z would be a point which is equal to a plus bi, where a is the real component and b is the imaginary component. And phi, the argument of z would be the angle from the x-axis to the ray going from the origin to wherever z is. That would be not theta, phi. Here I'm using that symbol. Okay? So that's the argument of z, that I have to measure that angle. And so the real component of z is equal to the absolute value of z cosine phi. And the imaginary component of z is equal to the absolute value of z sine phi. Okay? Okay? And z is equal to the absolute value of z sine phi. Of cosine phi. Absolute value of z times cosine phi plus I, absolute value of z sine phi. Okay? And if you factor out the absolute value of z, you get absolute value of z times cosine phi plus I sine phi. And that is the polar form of z. Okay, and so this is some complex analysis. Okay, and so this figure here on the length of this is the absolute value of z. And put a little arrow there as a vector. Okay, so the length of that vector is the absolute value of z, and that's the argument of z phi, real component of z a, imaginary component of z b. Okay, right, so this is the real component of z, and this is the imaginary component of c. And this is figure 5.3.1. Okay? Okay, so let's keep going. So this is some important facts about complex number z. Okay, definition 1. If n is a positive integer, so that means if n is a positive integer, then a complex n-tuple is a sequence of n complex numbers. V1, V2, Vn, where each of the v's from V1 to Vn are complex numbers. Okay, the set of all complex n-tuples is called complex n-space. And it's denoted by C to the n. Okay, scalars are complex numbers. And the operations of addition, subtraction, and scalar multiplication are performed component-wise. So if n is a positive integer, then a complex n-tuple is a sequence of n complex numbers, v1 to vn. The set of all complex n-tuples is called a complex n-space, denoted by c to the n. Scalars are complex numbers, and the operations of addition, subtraction, and scalar multiplication are performed component-wise. Okay, so that's definition 1. Okay. Okay, a complex n-tuple is just a list of n complex numbers. That's what that means, right? So if you had a list like 1 plus 2i, comma 3 minus 4i, comma 5, comma 8 plus 10i, that would be, I could put parentheses around it, that would be a complex 4-tuple, because it would be a list of 4 complex numbers. That's the first complex number, that's the second one, that's the third, and that's the fourth. A real number is a complex number because 5 is equal to 5 plus 0i. And so any real number is just a complex number whose real component is that number and whose imaginary component is 0. Okay, so a complex n-tuple is just a list of n complex numbers. Okay, and then if you take the set of all lists of n complex numbers, it's called n complex n-space. Okay, so and it's denoted by c to the n. Okay, so c to the n is just the set of all lists of n complex numbers. Okay, so as an example of Cn, C2 is the set of all complex 2-tuples. So C2 is the set of all ordered pairs of complex numbers. It's the set of all lists with 2 complex numbers in them. Okay. Okay, so that's definition 1. So now example 1. So let v equal v3 plus I, comma, negative 2i, comma 5. And a is equal to 1 plus I, negative I, 4, 6 minus 2i. Okay? So V is a complex 3-tuple, and this A is a 2x2 complex matrix. Okay? So V bar is just taking the complex conjugate of each component of that vector. Okay, and taking the complex conjugate of a complex number means keeping the real component the same and just negating the imaginary component. So the complex conjugate of 3 plus I is 3 minus I. The complex conjugate of 0 minus 2i is 0 plus 2i, or just 2i. And then the complex conjugate of 5, well, it's also 5. That's 5 plus 0i. Complex conjugate is 5 minus 0i, which is still 5. So that's the complex conjugate of a complex 3 tuple. And so in general, if you have a complex n tuple, you would just do the same thing with n components instead of 3. Okay, now if you take, and then if you look at the real component of v, where that's v, the real component would be 3 comma 0, comma 5, right? It would just be the real components of each, the real part of each component of v. That would be the real part of v. And then the imaginary part of v would be 1 comma negative 2 comma 0. These are the respective imaginary components of these. Okay? So that's the idea behind the real and imaginary components of a complex n tuple. And instead of 3 components, you could do it for any number n components. Okay, a bar is just taking the complex conjugate of each of these. So that's 1 minus I. That's negative 1. That's still negative 1. Complex conjugate of 4. And the complex conjugate of 6 minus 2i is 6 plus 2i. Okay, so the complex conjugate of a bar, is now the complex conjugate, so I did that right there. And then the real component of a is just taking the real component of each component of that. And then the imaginary component of a matrix would just be 1, 0, 0, negative 2. That would be the imaginary components of each of these entries, and you put them in their respective place there. Okay. Oh, that's negative I. It's negative I, so that's going to be 0. That's going to be 1. It's negative I, so the real component here is 0, and that's negative 1. Okay, so that example is showing you how to find each of these things. The complex conjugate of an n tuple, the real component of an n tuple, an imaginary component of n tuple, complex conjugate of a complex matrix, the real component of a complex matrix, and the imaginary component of a complex matrix. Okay, so those are 6 things you should be able to find. The 6 things I circled here. Okay? So know that for this section. And one other thing you should know, if you were, to take the determinant of A, which we'll try to fit in here, the determinant of A, you just compute the same way you would do a real determinant. This times this minus, for a 2 by 2 is this times this minus that times that. You get 1 plus I times 6 minus 2I minus negative I times 4. And so that's equal to 6 plus 4I. And then note that when I do I times negative 2I, I squared is negative 1. Okay, I squared is negative 1. And so when you do I times negative 2I, you get negative 2I times I squared. So I times negative 2I would be negative 2I squared. And then I squared is negative 1. So this would be negative 2 times negative 1, which is 1. So I times negative 2I is 1. And so this times this would give you a plus 1. And it would be minus negative 4, which would be plus 4. And so this would be 6, 7, 11 plus 4I. There. Wait. That's an I. I keep thinking that's okay, and then that's minus, this is an I there. So this would be minus negative 4I, that would be plus 4I. This would be 7 plus 8I. Plus, oh wait, that's 2. This times this is 2. Be plus 2. That's 8 plus 8i. Good. So the determinant of A is 8 plus 8i. Okay? And so you just calculate like you would a normal determinant of a normal matrix. Good. Inner product spaces. Okay, so for inner product spaces, this is chapter 6. Okay, so chapter 6 we're going to talk about now. We're going to talk about inner product spaces. So 6.1 is on inner product spaces. And so for definition 1 of 6.1, an inner product on a real vector space V is a function that associates each pair of vectors in V with a real number. Okay, so an inner product on a real vector space V is a function that associates each pair of vectors in V to a real number, and this is a number. Okay, this is a real number that is given that notation. Okay, so associates each pair of vectors in V to a real number that with each pair of vectors, I reset that. Okay, to a real number U comma V, such that for all vectors U, V, W in capital V and all scalars K, this is called the inner product of U and V. So the inner product of U and V is equal to inner product of V and U. That's called the symmetry axiom. 2, the inner product of U plus V and W is equal to the inner product of U and W plus the inner product of V and W. It's called the additivity axiom. The third one is the inner product of KU and V is equal to K times the inner product of U and V. That's the homogeneity axiom. And 4, the inner product of V with itself is greater or equal to 0. And the inner product of V with itself is 0 if and only if V is 0. That's called the positivity axiom. So a real vector space with an inner product is a real inner product space. Is a real inner product space. Okay? So definition 1, an inner product on a real vector space V is a function that associates each pair of vectors in capital V to a real number given that notation, such that for all vectors U, V, W, and capital V and all scalars K, the inner product of U and V is equal to the inner product of V and U. You can switch the order. That equation holds. Instead of the constant being here, you can move it outside there. And you can take the inner product of two vectors, it has to be greater or equal to 0. And if the inner product of a vector with itself is 0, that's equivalent to saying that vector is 0. Okay? Same truth value. So this statement, this equation, and this equation either both hold or both don't hold. Okay? And so if you take a real vector space, and you add to that real vector space an inner product, it's called a real inner product space, right? So if you have a set, if you have a set V, an operation of addition and an operation of scalar multiplication, that's your vector space, right? But then if you take your set and your two operations where all 10 axioms hold for a vector space, and then you add this function with these 4 properties to it called an inner product, and then you add the inner product function, which I guess you could just denote like this. If you add that to these list of these 3 things, now the team of these 4 things, this team together is called a real inner product space. Okay, so for just these three things, it's called a vector space. And then if you add this function with those four properties, the four of them combined now is called a real inner product space. Okay. Okay. So we have something called an inner product. It's a function. It's a function that if you look at a function as with a machine diagram like this, then if you think of that function, let's say I label this function like this, if the input is two vectors, u and v, right? U is the first vector, v is the second vector. If you input those two vectors in that order into this function called the inner product function, the output is the inner product of u and v, and it's a real number. And it's a function that satisfies these four properties. Okay, so you take any two vectors in some order, a first vector and a second vector, you put it into this function, and it spits out a real number, which we denote by that symbol. Okay, again, these four properties hold for that function. Okay, so these, okay, so if we define the inner product of u and v in Rn, so if u and v are in n space, the set of all n tuples, and we define the inner product of u and v as u1 v1 plus u2 v2 plus dot 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 plus un vn. That would mean, right, u is equal to the vector u1 comma u2 comma dot 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 comma un. V is equal to the vector v1 v2 comma dot 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 comma vn. Okay, so then these are the vectors u and v, and u1 to un are the components of u from the first component to the last component respectively. And so you just take the first component of u times the first component of v plus the second component of u times the second component of v plus the third component of u times the third component of v plus dot 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 plus the nth component of u times the nth component of v. You get that. Okay? Okay, and so that would be this would be an inner product, okay? It would satisfy all four axioms on the last board, okay? It would satisfy symmetry, additivity, homogeneity, and positivity, all four of those axioms in the last board. Okay? You don't need to know names, you can just know what they are. Okay? Okay? So we call Rn with this inner product, Euclidean inner product. Euclidean n space. Okay, so we call Rn with this inner product the Euclidean inner product. Euclidean n space. Sorry. So the inner product, this thing, is called the Euclidean inner product. Okay. So the name of the function is Euclidean inner product, and so Rn with Euclidean inner product is called Euclidean n space. Okay. Definition 2. So V is a real inner product space. Then the norm or length of a vector So if capital V is a real inner product space, then the norm or length of the vector little v in capital V is denoted by that symbol, and is defined by this. Okay, it's defined by that. So the norm or length of v is equal to square root of the inner product of v with itself. Okay, and the distance between two vectors is denoted by d of u comma v. And it's equal to the norm of u minus v, which equals to the square root of the inner product of u minus v with u minus v. Okay? A vector of norm 1, a vector with norm 1 is a unit vector. Okay? So if capital V is a real inner product space, the normal length of a vector little v and capital V is denoted by that symbol, and it's defined by the norm v is equal to square root of the inner product of v with itself. And the distance between two vectors is d of u comma v equals the norm of u minus v, which is equal to the square root of the inner product of u minus v with itself. A vector with norm 1 is a unit vector. Okay? So that just defines the norm of a vector or its length, and distance between two vectors and a unit vector. Okay, so that's definition. That's definition 2. Now let's keep going. So if u and v are vectors in a real inner product space, so if u and v are vectors in a real inner product space, capital V, and if k is a scalar, then these following A, the norm V is greater than 0 with equality if and only if V is equal to 0. B, the norm of KV is equal to the absolute value of K times norm of V. C, the distance between U and V is equal to the distance between V and U. And D, D of U comma V is greater than or equal to 0 with equality if and only if U equals V. Okay, so theorem 6.1.1 says if U and V are vectors in a real inner product space capital V, and if K is any scalar, then the norm of V is greater than 0 with equality if and only if V equals 0. The norm of KV is equal to the absolute value of K times norm of V. Distance between U and V is equal to distance between V and U, and the distance between U and V is greater than 0 with equality if and only if U equals V. Okay? So the part where it says with equality if and only if U equals V, that means that the statement D of the distance between U and V is equal to 0 has the same truth value as U equals V. Okay? So that's what this says. D, the distance between U and V is equal to 0 if and only if U is equal to V. Okay? Okay, so those two have the same truth value. That's what that last later part is. So the inner product between U and V is equal to W1 U1 V1 plus W2 U2 V2 plus plus W1 UN Vn. So that function defines an inner product on called the weighted Euclidean inner product. With weights W1, W2, dot, 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 WN. Okay? So that function defines an inner product on Rn called a weighted Euclidean inner product with weights W1 to Wn. Okay? Okay, definition 3. If capital V is an inner product space, then the set of points in capital V that satisfy the norm of U is equal to 1 is the unit sphere or unit circle in V. Then the set of points in capital V that satisfy the norm of U is equal to 1 is the unit sphere or unit circle in V. Okay? Okay, let's keep going. Okay, so in example 3, we're going to sketch the unit circle in R2 using the weighted Euclidean inner product, that guy right there. Okay, so we are going to sketch the unit circle with that Euclidean inner product. And so that looks weird, but we're just going to, the goal here is to find all vectors W such that the norm of W is equal to 1 with that weighted Euclidean product. Okay, so I'm not going to use W here, I just want W there for the goal. If U is equal to X comma Y, then the norm of U is equal to the square root of the inner product of U with itself, and that's equal to the square root of X squared plus Y squared. And so why is that? Because the inner product of U with itself is equal to the first component of U, which is X, times the first component of U, which is X, plus the second component of U, which is Y, times the second component of U, which is Y, which is X squared plus Y squared. The inner product of U with itself is X squared plus Y squared. And so that's why what goes in the square root is X squared plus Y squared. Okay? So we have the square root of, oh, sorry, it's with this weighted Euclidean product. Sorry. What's that? Okay, so the inner product of U with itself, defined here, is 1/9 X times X plus 1/4 Y times Y. Okay? So 1/9 times the first component of U, which is X, times the first component of the next vector is also u, which is x, plus 1/4 times the second component of u, which is y, times the second component of u, which is y. So you get 1/9 x squared plus 1/4 y squared. Okay, so that's the inner product of u with itself. So this is the square root of that, which is 1/9 x squared plus 1/4 y squared. Okay, so the norm of u is the square root of 1/9 x squared plus 1/4 y squared. Okay? And so if we're looking for where the norm of u is 1, that would mean that the norm of u, which is 1, is equal to the square root of 1/9 x squared plus 1/4 y squared. And if that means 1 is equal to this, so if you square both sides, you get the equation 1/9 x squared plus 1/4 y squared is equal to 1. Okay, so the values of x and y that satisfy that equation, 1/9 x squared plus 1/4 y squared equals 1, those are the points that this weighted Euclidean product has a distance 1 from the origin. And that would be the picture of an ellipse, where the length along the major axis, the major axis along x would be 3. It would go from -3 to 3, and then the y-axis would go from -2 to 2, and that would be a parabola right there. And so the points in that parabola would be the points x comma y. All the points x comma y in that parabola would be points that would satisfy that equation. Okay. So x squared over y plus y squared over 4 is equal to 1, right? That's the equation, just writing it out. And so if you think of this in the form of, you would look at ellipse, it's x squared over 3 squared plus y squared over 2 squared is equal to 1. And so that's how you get the length here is 3 and the length here is 2. And so that's how you get that ellipse from that equation, right? Okay, so that's pre-calculus. Okay, so that equation gives you all the points in that ellipse. That's a sketch of the unit circle in R2 using the weighted Euclidean product. So let A be an invertible So let A be an invertible n by n matrix, and U and V be vectors in Rn. Then phi, the inner product between U and V, is equal to AU dotted with AV, and that defines the inner product on Rn generated by A. Okay. So let A be an invertible n by n matrix, and U and V be vectors in n space. Then the inner product of U and V, defined as AU dotted with AV, defines the inner product on Rn generated by A. So AU times AV, okay? So 5, you can also write 5 as the inner product between U and V is equal to AV transpose AU. You could also write it as V transpose A transpose AU. Okay, so there's 3 ways here you can write it. You could write it like this, you could write it like that, or you could write it as that. All 3 of them are the same. Okay, so that's the inner product on Rn generated by A. That's another function where if all four properties for an inner product hold, and this function added to a vector space would create an inner product space, would form an inner product space. Okay. And so this equation, saying that this is equal to this, that's equation 6 in this section. Okay. Good. Example 6. So if little u is equal to capital U, little v is equal to capital V, our matrices in Rn. In capital M sub Nn, then the inner product of U and V is equal to the trace of U transpose V. That function defines the standard inner product. On capital M sub Nn. Okay, so if little u and little v are matrices in capital M sub Nn, which is the vector space of n by n matrices, then this function, which is equal to trace of U transpose V, defines a standard inner product on capital M sub Nn. Okay, but even though this looks like a weird function, this one, right, this defines that function. Even though it looks weird, it's actually very simple, and that's why it's the standard inner product on M sub N. So I'll show you what I mean. If capital U is this matrix, and capital V is this matrix, with those little v's as components, if those two are vectors in M capital M sub N, then what happens is that the inner product, so little u is that matrix capital U, little v is that matrix capital V. The inner product between U and V, using the standard inner product of capital M sub Nn, is equal to the trace of U transpose V. But what that turns out to be is U1 V1 plus U2 V2 plus U3 V3 plus U4 V4. Okay, so the inner product between these two matrices is equal to the sum of the products of their corresponding components. So you would take this component, multiply it with this one, then add this times this, and add this times this, and then plus this times that. And that sum of products is the inner product between matrices U and V with that standard inner product on capital M sub Nn. Okay? And also, the norm of U, which is equal to the square root of the inner product of U with itself, is equal to the square root of U1 squared plus U2 squared plus U3 squared plus U4 squared. Okay, so the norm of a matrix like this would be the square root of the sum of the squares of its components. Okay, so you would take each component and square it, each entry and square it, and it would sum up all the squares of those entries, and then take the square root of that sum. That's the norm of a matrix in M sub Nn with the standard inner product on M sub Nn. Okay, that's example 6. Okay, so in example 6, we see what the inner product is between two matrices, and the norm of a matrix is in this case. That's example 6. Example 7. So in example 7, if P is equal to A naught plus A1x plus A2x squared plus dot 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 plus ANX in N, and Q is equal to b naught plus b1x plus b2x squared plus dot 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 plus bn x to the n are polynomials in p sub n, then what I'm going to write below, which is 9, defines the standard inner product. On p sub n. Okay, so if you have those two polynomials in p sub n, then this equation 9 will define the inner product between those two polynomials in p sub n. That's the inner product of p and q is equal to a naught b naught plus a1 b1 plus dot 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 plus an bn. Okay, so that defines the standard inner product on p sub n. Okay, and the norm of p is equal to the square root of the inner product of p with itself. And that's equal to the square root of a naught squared plus a1 squared plus dot 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 plus a sub n squared. Okay, and this is the norm of a polynomial relative to this inner product. Okay, so this is the norm slash length of polynomial p relative to the standard inner product on p sub n. So we define the norm of something using an inner product. And so when we talk about the norm of a vector in a vector space, it's relative to, we take the norm of a vector in an inner product space. It's relative to the inner product function that you're using. And so here we're using the standard inner product on p sub n. And so when we find the norm of p, we get this, but it's relative to the standard inner product on p sub n. If we define a different inner product, a different function for our inner product space, p sub n, then for a different inner product function, we would get a different norm of p. And that's fine. But it would be the norm of p relative to that different inner product function. Okay? So for this inner product function, there can only be one norm. It's unique. And we found it. Okay? But we would be specific about what norm we found. We found the norm of p relative to the standard inner product on p sub n. Okay? Let me just get that. Okay, so let's keep going. So we're going to example 8. Okay, so example 8. If p is equal to p of x, which is equal to a naught plus a1x plus a2x squared plus dot 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 plus an x to the n, and q is equal to q of x, which is equal to b naught plus b1x plus b2x squared plus dot 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 plus bn x to the n, are polynomials in p sub n. They're in p sub n, polynomials in p sub n. And if x naught to xn are distinct real numbers, then the inner product of p and q is equal to p of x naught times q of x naught plus p of x1 times q of x1 plus dot 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 plus p of xn q of xn. Okay? that defines an inner product on P sub n. Defines the evaluation inner product. At x naught x1 to xn. And that's an inner product on P sub n. It's an inner product on P sub n, because that's the vector space we're talking about, P sub n. Okay? So P and Q are polynomials in P sub n, and x naught to xn are distinct real numbers. Then that function defines the evaluation of inner product in x naught to xn. Okay? So so given the polynomials P and Q, you find their inner product, but you also have to consider these n plus 1 real numbers, x naught to xn. Okay? Okay, and so it depends on those values also. Okay, and so the norm of P relative to this inner product, right, because every norm is defined by an inner product, right? Here we're defining the norm as the square root of the inner product of P with itself. That's equal to the square root of P of x naught squared plus P of x1 squared plus dot 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 plus P of xn squared. Okay? Because here, instead of Q, it would be another P. And so it would be P of x naught times P of x naught plus P of x1 times P of x1 plus dot 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 plus P of xn times P of xn. And so you get P of x naught squared plus P of x1 squared plus dot 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 plus P of xn squared. And that would be what would go inside the square root there, that sum of squares. Okay, so norm of P is the square root of the sum of those squares. Okay, and that's equation 11. Okay? Okay, that's the norm of polynomial P relative to the evaluation of the product. Okay, relative to the evaluation in a product. Okay, so with this we have another inner product, and we have the norm relative to this new inner product. That's example 8. Okay, so Theorem 6.1.2. If U, V, W are vectors in capital V, which is a real inner product space. Okay. And K is a scalar. Then we have the following. A, if the inner product of 0 with V is equal to the inner product of V with 0, which is 0. B, the inner product of U with V plus W is equal to the inner product of U and V plus the inner product of U and W. C, the inner product of U and V minus W is equal to the inner product of U and V minus the inner product of U and W. D, the inner product of U minus V and W is equal to the inner product of U and W minus the inner product of V and W. Okay, and then E, K times the inner product of U and V is equal to U, the inner product of U, and KV. Okay, so Theorem 6.1.2. If U, V, W are in a real inner product space capital V and K is a scalar, then these 5 equations hold. Okay? This is just like additivity, except in the second component. And then you're doing subtraction here. Okay, now you have subtraction in the first component. And then here, the other one had k moved to the first component. Now we're moving k to the second component. That's how E is different from the homogeneity property when we define it in a product space. Okay, that property said that k times the inner product of u and v is equal to the inner product of ku and v. It's called the homogeneity property of inner product space. Is one of the four conditions that have to hold in order to say that your function is an inner product function. But this is slightly different because now we're saying that k goes in the other component. Okay, and so that needs to be said, but it is in this theorem. Okay, and with this proof, you can now say that in any mathematical proof. Now, okay, so that's the end of 6.1, and let's keep going to 6.2. Okay, so 6.2 is on angle and orthogonality. In inner product spaces. Okay, so angle and orthogonality in inner product spaces. And so, first off, we know theta is equal to cosine inverse of the norm of u. Theta is cosine inverse of u dotted v with v over the norm of u times norm of v. Okay, and because we know that, we can say that -1 is less than or equal to u dot v over the norm of u times norm of v, which is less than or equal to 1. That's point 2 in this section. Okay, and because we can say this, fact 2, we have theorem 6.2.1, which is the Cauchy-Swartz inequality. So if u and v are in vectors in a real inner product space capital V, then the absolute value of the inner product of u and v, and that's the absolute value of the inner product of u because of this equation, is less than or equal to the norm of u times norm of v. Okay, so that's fact 3 in this section. That's Cauchy-Swartz inequality. So you have vectors u and v in a real inner product space capital V, then the absolute value of the inner product of u and v, which is u dot v here. So the inner product of u and v, that's another way of, u dot v is another notation for the inner product between u and v. Okay, and so here it's saying the inner product this is less than, if you take the absolute value of this, then you would say that this, the absolute value of this is less than or equal to 1. It's the absolute value of the inner product of u and v is less than or equal to norm of u times norm of v by algebra. Okay, and so that's the Cauchy-Swartz inequality. Okay. Next, if you take the inner product of u and v and you square it, it's less than or equal to the inner product of u with itself times the inner product of v with itself, and that's fact 4. Now, if you take the inner product between u and v and you square it, that's less than or equal to the norm of u squared times the norm of v squared. Okay, and that's fact 5. Right, because the inner product between u and itself is the norm of u squared, and the inner product of v with itself is the norm of v squared. And so you're just rewriting this as this, and that is that. Okay, so 5 that you can deduce 5 directly from 4. Okay, so here theta, which is cosine inverse of u dot v, right, this symbol, the inner product between u and v divided by the norm of u times the norm of v, is the angle between u and v. So if you have a vector u and a vector v, then theta is the angle between them. Okay, that's this theta. Okay, example 1 if the vector u, which is the matrix capital U, which is the matrix 1, 2, 3, 4, and the vector v, which is matrix capital V, is the matrix negative 1, 0, 3, 2, then let's say we want to find theta, the angle between them. Well, theta is cosine inverse of the inner product between these two vectors divided by the product of their norms. So we need to find three things. We need to find the inner product between u and v. We need to find the norm of u. We need to find the norm of v. And we just need to substitute those three things into that formula to get theta. So to find theta, we just find this, and that, we plug in. Okay, so when you find the inner product between u and v, you can get that's the square root of 1 times this times this plus 2 times 0 plus 3 times 3 plus. Okay, so then negative 1, 8, 16. So that's the square root of 16, which is 4. Okay, so then oh, sorry. So the norm of u of v is not the square root of that. It's just the sum of those products, right? And so you get that that's equal to 16. Okay, so that's 16. So then the norm of u, is just the square root of the inner product of u with itself. And so when you calculate that, you get the square root of 30. Okay, and when you calculate the norm of v, you get the square root of 14. Okay, so the inner product between u and v is 16, the norm of u is 30, and the norm of v is square root of 14. So the norm of u is the square root of 30. So you get those three numbers, and then so when you find theta, and so if you were to find cosine theta would be the norm of u and v over the length of u times the length of v. And that would be 16 over the square root of 30 times the square root of 14. And that would be 0.78. Okay, so cosine of theta would be 0.78. If you want to find theta, you could just do cosine inverse of 0.78. Okay, that will give you theta. Okay. Okay, so you just find this, and that, plug in, and solve for theta, that equation. Okay, so next. Okay, theorem 6.2.2. Okay, so if u, v, and w are in a real inner product space capital V, and if k is a scalar, then the following are true. A, the norm of u plus v is less or equal to the norm of u plus the norm of v. And B, the distance between u and v is less or equal to the distance between u and w plus the distance between w and v. So this is the triangle inequality for norms, and this is the triangle inequality for distances. These are the names of those two inequalities. Okay, and that's theorem 6.2.2. Okay, so if you have three vectors in a real inner product space capital V and k is a scalar, those two inequalities hold. Okay? Definition 1. Two vectors, if little u and little v are vectors in inner product space capital V, so U and V in an inner product space capital V is orthogonal if the inner product between U and V is equal to 0. Okay, so that's definition 1. Okay, next, Theorem 6.2.3. So this is called the generalized theorem of Pythagoras. If U and V are orthogonal vectors in real inner product space capital V, then the norm of U plus V squared is equal to the norm of U squared plus the norm of V squared. So this is basically a general version, more general version of the Pythagorean theorem. Okay, so then if U and V are orthogonal or perpendicular in a real inner product space capital V, then the norm of U plus V squared is equal to norm of U squared plus norm of V squared. Generalized theorem of Pythagoras, Theorem 6.2.3. Okay, so saying that U and V are orthogonal means that their inner product is 0. So if you have two vectors whose inner product is 0 and they're in a real inner product space capital V, that equation holds. Okay, next. Definition 2. If W is a subspace of a real inner product space capital V, then the set of all vectors in capital V that are orthogonal to every vector in W is the orthogonal complements it's called the orthogonal complement of W, and it's denoted by W with the superscript perpendicular sign. Okay, so capital W is a subspace of the real inner product space capital V. Then the set of all vectors in capital V that are orthogonal to every vector in W is the orthogonal complement of W, denoted by that symbol. Right? And so if you were to think of the standard inner product, in R3, and you had a plane here through the origin, because the plane through the origin is a subspace of R3. Right? The origin itself, that point, a line through the origin, a plane through the origin, all of R3, those are the subspaces of R3. So that plane through the origin is a subspace of R3. And then if you look at a line going through the plane that's perpendicular to it, so if you get a line here that's perpendicular to the plane, then all vectors on that line are perpendicular to every vector in this line, orthogonal, because the inner product of any vector on this line with any vector here would be 0, using the standard inner product on vectors, okay? So if you had the standard inner product on R3, then the line going through this plane perpendicular to it, all the vectors on that line would be the orthogonal complements of the subspace W in R3. Okay, this plane would be the subspace W, and then the line, all the vectors on this, all the line perpendicular to that plane through the origin, that would be W complement. Okay, and again, these vectors are, the fact they're perpendicular to this plane is determined by the fact that any vector u on the plane and any vector v on this line, if you found the inner product of u and v, it would be 0, but that would be from the inner product you defined here, which would be the standard inner product. R3. Okay? Okay. Theorem 6.2.4. If W is a subspace of a real inner product space capital V, then W complement is a subspace of V. And V, the intersection of W and its complement, W and W complement, is the 0 set. Okay? Theorem 6.2.5. If W is a subspace of a real finite dimensional inner product space capital V, then the orthogonal complement of W, the orthogonal complement of the orthogonal complement of W is W, or W perp is equal to W. That's something we could say is perp. Okay, so that's theorem 6.2.4 and theorem 6.2.5. Okay, let's keep going. Example 6. So let W be the subspace of R6 spanned by the vectors (1, 3, -2, 0, 2, 0). W2 is equal to 2, 6, -5, -2, 4, 3. W3 is equal to 0, 0, 5, 10, 0, 15. And W4 is equal to 2, 6, 0, 8, 4, 18. Okay, so W is going to be the subspace of 6 space, R6, spanned by those 4 vectors, those 4 sextuples. And we want to find a basis for the orthogonal complement of W. Okay, so we want to find a basis for the orthogonal complement of W. And so to do that, just make a matrix whose rows are those 4 vectors. And so W1 is going to be row 1, 1, 3, -2, 0, 2, 0, 2, 6, -5, -2, 4, -3, 0, 0, 5, 10, 0, 5, 15, and 2, 6, 0, 8, 4, 18. So now the rows of that matrix, right? This is the first row, that's W1. The second row is W2. The third row is W3, and the fourth row is W4. Those are the 4 vectors there, right? W1, W2, W3, W4. So you take that and just just find the null space of this matrix A. So here's A, and find the null space. And so here's the fact. The row space and null space of a matrix are orthogonal complements. Okay, so the row space and null space of a matrix are orthogonal complements. And so the row space is just the span of the rows of this matrix. Okay? So the row space is the span of the rows of A, right? Is the span of the rows of A, but the rows of A are W1, W2, W3, and W4. Because I made the rows of this matrix, those four matrices, and the row space is the span of the rows of that matrix. The row space of that matrix is the span of those six tuples. The span of a set of vectors is the set of all linear combinations of those vectors, right? And so the row space of A is the set of all linear combinations of those four vectors, or the span of those four vectors. And we want to find a basis for the orthogonal complement of that subspace of R6. Okay? Well, the null space of this matrix is orthogonal to the span of those four vectors, because the span is also the row space of that matrix. And so the null space of this matrix is the set of solutions to the equation AX equals 0. Okay? So the solutions are the six tuples X, such that A times X equals 0. And so if you find the general solution to AX equals 0, you're finding the null space of that matrix. And so the general solution of AX equals 0, the set of all solutions X to this matrix equation, that's the null space, and it's the orthogonal complement of the span of those four vectors. And so when you find the null space of AX equals null space of A, you find a vector space and then a basis for that vector space. The basis for the null space of A is the basis of the orthogonal complement of A. Okay? And so you get as a final answer, a basis is V1, which is negative 3, 1, 0, 0, 0, 0. V2, which is negative 4, 0, negative 2, 1, 0, 0. And V3, which is negative 2, 0, 0, 0, 1, 0. Okay? So those three vectors form a basis for the null space of A. And so they form a basis for the orthogonal complement of the row space of A. By this fact, the row space and null space of a matrix are orthogonal complements. Okay? And so that's the answer. That's the basis. Those three vectors form a basis for the orthogonal complement of the subspace of R6 spanned by those four vectors. Okay? So that's example 6. And that's the end of 6.2. And so let's go to 6.3. So 6.3 is the Gram-Schmidt process. Okay? So 6.3 is on what's called the Gram-Schmidt process. Okay? So definition 1. A set of two or more vectors in a real number product space is orthogonal if all pairs of distinct vectors in the center are orthogonal. An orthogonal set consisting of only unit vectors or vectors with norm 1 is orthonormal. So an orthogonal set consisting of only vectors with length 1 or only unit vectors is an orthonormal set. Okay, an orthogonal set is one where if you take any two vectors in the set, they're orthogonal. An orthonormal set is an orthogonal set in which every vector has length 1. So that's the definition of an orthogonal set and an orthonormal set. Okay, example 1. Let v1 equal to the vector 0, 1, 0. v2 is going to equal to the vector 1, 0, 1. And v3 is equal to 1, 0, negative 1. And assume R3 has the Euclidean inner product. Okay, so let those three vectors, so assume you have those three vectors and assume R3 has Euclidean inner product. Then that set S, v1, v2, v3 is orthogonal. Since the inner product of v1 with v2 is equal to the inner product of v1 with v3, which is equal to the inner product of v1 with v2, which is equal to 0. Basically, if you take the inner product of this vector with that vector, you get 0. If you take the inner product of this vector with that one, you get 0. If you take the inner product with this vector and this vector, you get 0. That's v2 and v3. Okay, and then if you switch the order, they're the same because the inner product function has a property called symmetry, where you can switch the order and the value is the same. Okay, and so there's 6 ways to order these, choose 2 of these vectors and assign order of those 2 vectors. And so there's these 3, and you could flip any one of the 3 and it's still 0. So all 6 are 0. And so this set S is orthogonal. That's the conclusion of example 1. The set formed by those 2 vectors is an orthogonal set. Okay? That's from the definition 1 of a definition of an orthogonal set. So the process of multiplying a vector v by the reciprocal of its length to get a unit vector in the same direction as v is called normalizing v. Okay, so the process of multiplying a vector v by the reciprocal of its length to get a unit vector is in the same direction as v is called normalizing v. Okay, so if you have a vector v like this, okay, then to normalize v would be to find the length of v and divide it by its length. find the length of v, then take v, divide it by its length. And then you would be scaling the vector v so that instead of having length v, it now has length 1. And you would get the vector u that has length 1 and it's in the same direction as v. Okay, so finding this vector u, which is in the same direction of v of length 1, is called normalizing v. Okay, we're finding that vector v. U, which is equal to v divided by the length of v. That's the same as saying taking v and multiplying it by the reciprocal of its length, right? The reciprocal of its length is 1 over the norm of v. So v times the reciprocal of its length is v times 1 over the norm of v, or v divided by norm of v. Okay? Okay, so if you're given an orthogonal set, okay, so if you're given an orthogonal set, then all you have to do is divide each vector in that set by its length. Then the resulting vectors form an orthonormal set. So divide each vector in that set by its length, and the resulting vectors form an orthonormal set. Okay, so an orthogonal set, then divide each vector in that set by its length, then the resulting vectors form an orthonormal set. Okay, so that's it. Yeah. So if you have a set of vectors, and it's an orthogonal set, divide each vector by its length. And now you have an orthogonal set in which every vector is length 1, and that's an orthonormal set. Good. Normalize V3 is equal to okay, so the norm of V3 there is just the square root of the sum of the squares of its components. So the norm of V3 is the square root of 1 squared plus 0 squared plus negative 1 squared, that's the square root of 2. Okay? And so to normalize V3, you just take U3, which is V3 divided by its length. So that's the vector V3, 1, 0, negative 1, divided by the square root of 2. That's 1 over the square root of 2, comma, 0, comma, negative 1 over the square root of 2. Okay, so U3 is that vector there. So theorem 6.3.1 is if the set S is equal to... So if that set S is an orthogonal set, so is an orthogonal set of non-zero vectors. In an inner product space, then capital S is linear. So if that set S is an orthogonal set of non-zero vectors in an inner product space, then S is linearly independent. Okay, so that's theorem 6.3.1. So if you have an orthogonal set of non-zero vectors, and they're all orthogonal to each other, or perpendicular to each other, with your given inner product function, then S is a linearly independent set. That's theorem 6.3.1. So in an inner product space, a basis consisting of orthonormal vectors is an orthonormal basis. And a basis consisting of orthogonal vectors is an orthogonal basis. So in an inner product space, a basis consisting of orthonormal vectors is an orthonormal basis, and a basis consisting of orthogonal vectors is an orthogonal basis. Okay, so in an inner product space, a basis consisting of orthonormal vectors is called an orthonormal basis, and a basis consisting of orthogonal vectors is an orthogonal basis. Okay, I guess that's the definition of those two bases. Going, theorem 6.3.2. So if that set S is an orthogonal basis for an inner product space, capital V, and if U is any vector in capital V, then U comma V1, the inner product of U and V1 over the norm of V1 squared, V1 plus the inner product of U and V2 over the norm of V2 squared, V2 plus dot 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 plus the norm of U and Vn over the norm of Vn squared, Vn. Then U is equal to that. Okay, so on. Okay, so if that set S is an orthogonal basis for an inner product space V, and if U is any vector in capital V, then U is equal to this. Okay, so this is the basis S. It's V1, V2 to Vn. Those are the n vectors in that set. Here's V1, here's V2, here's Vn. You're taking your vector U, and you're saying it's equal to this expression. And so you're taking U and you're taking the inner product of U, which each of those n vectors, and those are the numerators of those n fractions. And then in the denominator, you're taking the norm of those vectors respectively. So in the denominator of the first fraction, you get the norm of V1 squared. In the denominator of the second fraction, you get the norm of V2 squared. And in the denominator of the nth fraction, you get the norm of Vn squared. Okay? And so you take those fractions, you multiply them correspondingly with the vectors V1 to Vn. So in the first fraction, it's multiplied by V1, the second fraction multiplied by V2, so on, the nth fraction multiplied by Vn. We add up those n's products, and you get that's equal to U, okay? And it's assumed that that set S is an orthogonal basis for that inner product space, capital V. Okay? Okay, and again, U is any vector in your inner product space, capital V. So you can take any vector U and express it in this way. Okay? So this is not hard to memorize because all the terms are very similar. So if you memorize this first term, the only thing that changes is the subscript, right? So the norm of U and V1 over the norm of V1 squared V1 plus the norm of the inner product of U and V2 over the norm of V2 squared V2 plus the inner product of u and v3 over the norm of v3 squared, v3, and so on. And so you're just doing the same thing, and you're doing it n times, where you're just changing the coefficient of v in each one, and u is staying the same. Okay? And so you just have to apply some memorization techniques here to remember this expression, and you're saying that u is equal to that. Okay? So you need to spend some time memorizing that, memorizing 3. So that's part A of this theorem. And part B, so S of that set is so if that set is an orthonormal basis for an inner product space capital V, and if u is any vector in capital V, then u is equal to the inner product of u and V1 times V1 plus the inner product of u and V2 times V2. Inner product of u and Vn. So okay, so if that set S is an orthonormal basis for an inner product space V, and if u is any vector in capital V, then you get that equation. So if that set S, right, is an orthonormal basis, okay, that means that it's an orthogonal set and every vector is length 1, okay, right? It's an orthogonal set because you take any two vectors that are orthogonal. If you take any two vectors in that set, their inner product is 0. So it's an orthogonal set. Again, it's orthonormal because in addition to being an orthogonal set, the length of every vector is 1. The norm of each vector is 1, and the norm is determined by the inner product you chose for that inner product space. Okay, so you have an orthonormal basis, and it's a basis. So it's a linearly independent set, and it spans the vector space V that you're talking about. Okay, so this is an orthonormal basis for your inner product space V. And if u is any vector in capital V, then you can say that vector u is equal to that sum of products. Okay? It's just this expression except without the denominators. And that's because each denominator is the norm of each vector squared. But if each vector is length 1, the norm squared, the length squared is also 1. And so if you know that all these vectors have length 1, you don't need to square the norms in the denominator because you're just getting 1. And so that's why you can leave out the denominators in each term. Okay, so to this comes directly from this, where you just get rid of the denominators because you're just dividing each term by 1, by squaring the 1 squared in the denominator, 1 squared in the denominator. You don't need that there. And so that's why you can have this equation 3. This equation 4. Okay? And so this is theorem 6.3.2, that's part A and that's part B. Okay, so given the S here, this set, so that set S is equal to that set is an orthogonal basis. Okay, so given that set is an orthogonal basis, then the coordinates of u relative to S is equal to this. Okay, so here's formula 6. It says the coordinates of u relative to S is that n time. where that set S is an orthonormal basis. Okay? And given that same S, V1 to Vn is an orthonormal basis, the coordinates of U relative to S is equal to this vector. Okay, is equal to that untuple. And so what in the world am I saying? Well, basically, if from the last board we showed that U is equal to the inner product of U and V1 over the norm of V1 squared V1 plus the norm inner product of U and V2 over the norm of V2 squared V2. Okay, so if you can express U like that, then basically the coordinates of U relative to S would be C1, comma C2, comma dot dot dot, comma Cn, where C1 is the coefficient of V1 there, C2 is the coefficient of V2 there, and Cn is the coefficient of Vn. Because the coordinates of U relative to S is equal to this, where U is equal to C1 V1 plus C2 V2 plus dot 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 plus Cn Vn. And so in order to find the coordinates of U relative to S, you just need to express U as a linear combination of the vectors in S. And when you do that, you find the coefficients, the first to nth one, and those are the first to nth components respectively of the coordinates of U relative to S. And so looking at this linear combination and looking at that expression of U, you can see there's an obvious correspondence between the coefficients of the V's and these terms here. Just C1 is this, C2 is that, and Cn is that. This is the coordinates of U relative to S is right there. Okay, and if you have an orthonormal basis here, then the norms of each vector is 1. And so you're dividing by 1 each time, and so there's no denominator of 1. And so you just get the numerators for each one. Okay, you still get these as the components, but now the denominators are all 1 squared, and so you don't need that, you're off with that. Okay, so that's that. Let's keep going. Okay, so example 5, let V1 equals 0, 1, 0. V2 is equal to negative 4/5. Okay, so V1, V2, and V3 are those vectors, okay? And so this set S here, V1, V2, V3, is an orthonormal basis. For R3 with the Euclidean product. So those three vectors there, they form an orthonormal basis for R3, okay, with the Euclidean inner product, right? Okay, so that means they all have rank 1, they're each orthogonal to each other. So if you take any two, their inner product is 0, they're orthogonal. If you take any pair of vectors that are orthogonal, the length of all of them is 1. They form a basis for R3, because they're linearly independent and they span all of R3. So, sorry, excuse me. So S is an orthonormal basis for R3 with Euclidean inner product. Okay, so the goal here is going to be to express U equals 1, 1, 1 as a linear combination of the vectors in capital S. And find the coordinates of U relative to S. Okay? Okay, so what we're going to do then is U is going to equal the inner product of U with V1 over the norm of V1 squared, V1, plus the inner product of U and V2 over the norm of V2 squared, V2, plus the inner product of U and V3 over the norm of V3 squared, V3. Okay, so that's U with that formula, right? And so we have an orthonormal, S is an orthonormal basis for R3. Okay, so we have a set S here with V1, V2, and V3. Okay, the V1, V2, V3 is there. And so you just compute the inner products and you plug them in. Okay, so the inner product of U and V1, when you compute it, is 1. The inner product of U and V2 is equal to negative 1/5. And the inner product of U and V3 is equal to 7/5. Okay, so you just plug them in. So the inner product of U and V1 is 1 over, now the norm of V1, it's orthonormal. The length of everything is 1. So it's 1 over 1 squared V1 plus negative 1/5 over 1 squared V2 plus 7/5 divided by 1 squared V3. And that's equal to 1 V1 minus 1/5 V2 plus 7/5 V3. Okay. Okay, so when you calculate this, it's 1. When you calculate this, it's negative 1/5. When you calculate this, it's 7/5. And you just plug them in. And the lengths of every vector is 1 because it's an orthonormal set. It was given as an orthonormal set. Or you could find the norms and it's 1. Okay? And so then you just get that U, the vector U, is equal to 1v1 minus 2v2 plus 7/5 v3. Okay, so we use that when we found these inner products. We plug them in here. So the coordinates of U relative to set S is 1, negative 1/5, 7/5. So that's the coordinates of U relative to that set S. Okay, and we expressed U as one of the combination of the vectors v1, v2, and v3 here, and we found the coordinates there. So we did this, and we expressed that as a linear combination of the vectors in X there. So we did both those things. No problem. Okay. Okay, almost done. Okay, let me check something. Good. Okay. Working. Okay. Theorem 6.3.3. It's projection theorem. And so if W is a finite dimensional subspace of an inner product space capital V, then every vector little u in capital V can be expressed in exactly one way as u equals W1 plus W2. That's equation 8. Okay? Where W1 is in capital W and W2 is in W perp. Okay, so the orthogonal complement, you can use this notation, and the superscript here, you could say perp, so it's in W perp. Case W is a finite dimensional subspace of an inner product space V. Okay, being a finite dimensional vector space means its basis is formed by finitely many vectors, right? And it's a subspace of your inner product space V. Then every vector u in capital V can be expressed in exactly one way as u equals W1 plus W2, where W1 is in capital W and W2 is in its orthogonal complement. Okay? So the same example I keep using, I'll use it again. If we're in R3, we have a plane going through the origin. Okay? Here's a plane through the origin. That's a subspace of R3, where R3 is an inner product space. The inner product function is just the standard inner product in R3, where you multiply the corresponding components of 2, 3 tuples and you add up the products. That's the standard inner product on R3. Okay, so you have this plane through the origin. It's a subspace of R3. And so if you look at the line going through that plane, perpendicular to that plane, all the vectors again on that plane make up the orthogonal complement of the subspace W of the plane. So W is the plane for the origin. W complement is the W perp is the orthogonal complement, which is that line for the plane. Okay, and so it's saying that every vector u in R3. So if I put u all the way over here, that's not in the plane and not in the line, I can express that as in exactly one way as a vector in W this is the plane, as a vector in W, because this continues out in direction, as a vector in W plus a vector in W perp. So this would be W1 here. That would be W1 is in W, and W2 is a vector on this line that's translated so that the initial point, instead of being at the origin, is at the terminal point of W1. And that would be W2. Okay? So this W1 and this W2, these two vectors are orthogonal because one is in W, one is in the orthogonal complement of that subspace W. And so W1, W2, W1 is in W and W2 is in W perp. And W1 plus W2 is that vector U. So any vector U in R3 can be expressed exactly one way as a vector W1 in W1 in the subspace W and W2 in its orthogonal complement. Okay, that's called the projection theorem. And this W again has to be a finite dimensional subspace. And in this case it is, because this is a two-dimensional subspace of R3. A plane is two-dimensional. And it's finite dimensional because the plane has a basis consisting of exactly two vectors. That's what makes it two-dimensional. And so it's finite dimensional because 2 is a finite number. Okay? Okay, so that's the projection theorem. So W1 is the projection of U onto W, and W2 is the projection of U onto W perp in formula 8, in the last formula. Okay? The one where I said U is equal to W1 plus W2 in the projection theorem, where W1 is in, this is in W, and this is in W perp, right? Exactly one way. So that W1 is the projection of U onto W. W2 is the projection of U onto W perp. Right, so I'm going to draw the same picture again. We're in R3. Here's R3. Here's our subspace, which is the plane through the origin, which is is a two-dimensional finite two-dimensional subspace of R3. This plane W3 origin. Then the line, I'm just gonna have it maybe go this way, make the plane inclined a little bit more. This is a W perp. And so if I have a vector U here, here's U, then W1 is the projection of U onto W. This is W. And so if I were to project, let's say the projection of U onto W is that. That's the projection of U onto W. And then this is the and then if you looked at this vector, this is the vector I would have to add to W1 to get the W2, but I would put that on W perp. That would go here. So this vector here, this is the W2 in W perp. This is W2, it's just it's this vector translated so it's on that line. That's the projection of U onto W perp. Okay, so that's what that means. It's kind of like in the two-dimensional case where we were looking at the matrices where we had a vector where we had something here, and if we took this vector, it would be the projection of U onto the x-axis, and if we looked at this vector, it would be the projection of U onto the y-axis. So this is the projection of U onto the x-axis, this is the projection of U onto the y-axis, right, this vector. So similarly, here the projection of this vector onto the subspace W is this vector, and the projection of U onto W perp is that vector. Okay, you can see how, in a simpler way, you get these two are very similar. Okay, it's this idea in this a little bit more complicated of a situation. Okay. Okay, so U is equal to the projection of U onto W plus the projection of U onto W perp. That's equation 10. Okay. So instead of W1 plus W2, we're using that notation. And so U is equal to the projection of U onto W plus U minus the projection of U onto W, which is, I don't want to say obvious, but I do want to say obvious, right? If you're taking this and you're taking plus U minus that, these cancel and you get U, right? Okay, so then that's equal to that. Whatever this thing is, right? If you don't understand what this is, whatever that is, it's this plus U minus the same thing. They cancel. Okay. But this thing is the projection of U onto W perp. They're equal. They're the same. Okay. And then, almost done. Theorem 6.3.5. Every non-zero finite dimensional inner product space has an orthonormal basis. Okay, so every non-zero finite dimensional inner product space has an orthonormal basis. Okay, so if you have a non-zero finite dimensional inner product space, it's also a vector space, so it has a basis. But then in addition to having a basis, we know that we can also find a set that has more conditions than just a basis has. We can find a set that is a basis, that's also an orthogonal set, and every vector in the set has length 1. That would be an orthonormal basis, right? It would be a basis plus an orthogonal set, and consists only of unit vectors. Okay, so every vector space has a basis. And so it being a non-zero finite dimensional inner product space, it's a vector space as an inner product space. And so we would have that it has a basis already. But now we're going further and saying that, not in addition to saying it has a basis in which that is an orthogonal set and consists only of unit vectors. Okay, so this is adding more to just the fact that every vector space has a basis. Okay? Okay. And so what I'm going to do now is show you what's called the Gram-Schmidt process. So the Gram-Schmidt process. So to convert a basis U1, U2 to U sub R into an orthogonal basis, perform the following computations. So to convert a basis like that into an orthogonal basis like that, we want to perform the following computations. Okay? So we already know every vector space has a basis, and so when we have a finite dimensional inner product space, and we want to find an orthonormal basis for it, which we know exists by the last theorem. So we know an orthonormal basis exists, and if we already have a basis, there's a way to convert any basis to an orthonormal basis. Okay? And so that will show how the last theorem is true. Okay, so we're going to start with the basis for a vector space, which is also an inner product space, and this procedure will convert that basis to an orthonormal basis. Okay, and so just follow these steps. Step 1. V1 is equal to U1. Okay? So the first, you're going to make an orthogonal, we're going to make an orthogonal basis first. So we're taking a basis and converting it to an orthogonal basis. Okay, so the process is basis to orthogonal basis. Basis to a basis in which you take any two vectors in a set and they're orthogonal. Their inner product is 0. Okay, so step 1 is that the first vector in your new orthogonal basis is going to be the same as the first vector in your original basis. Step 2 is going to be the second vector in your new orthogonal basis is going to be U2, the second vector in your old basis, minus the inner product with U2 and V1 over the norm of V1 squared V1. Okay, so V2, following this formula, V2 is going to equal this. You'll make that the second vector in your orthogonal basis. Step 3. So step 3 is V3 is going to equal U3 minus the inner product of U3 and V1 over the norm of V1 squared V1 minus the inner product of U3 and V2 over the norm of V2 squared V2. And so that's V3. Okay, so all we did was, now for V2, I'm just subtracting one complicated term. For V3, I'm going to subtract two complicated terms. In step 4, I'm going to take V4, and it's going to be U4, and it's going to be a subtraction of 3 weird terms. Okay, and so what you're doing is, for instance, if you have V4, right, your first term is going to be U4. It's going to be the fourth vector in your old basis. And you're going to take that fourth old base thing, you're going to take the inner product of that with the first vector in your new basis, which you already found. And this is the previous one. And then you're going to do over the norm of v1 squared times v1. Then u4 again, keep using u4, and now you're going to go to the next vector in your new basis, take your product of that with u4 with v2 over the norm of v2 squared v2, then minus u4 again, then you're going to take the next new vector in your new basis before v4, and you're taking your product of u4 with v3 over the norm of v3 squared v3. And so when you're finding v4, you've already found v1 to v3. And so for each of the vectors v1 to v3, you're going to have a term where you subtract a thing that looks like this, one for each of those v's. Here you're using v1 here you're using v2, here you're using v3. Those are the vectors before v4 there. For v3, there's v1, v2, and this term was for v1, and this term was for v2. Make sense? And for v2, the only one before it was v1, and so there's only one term, this weird term like that, to subtract there. Okay? But there's a clear pattern, and you just follow that pattern, and then you continue these steps until the rth step. Okay, and it's step R, I'm calling it, because we're dealing with sets with R vectors in them. And so you're going to have to follow these R steps because you're going to have to find R new vectors for your new orthogonal basis, right? You're converting a set with R vectors in it into another set with R vectors in it. And so you're creating a set with R vectors, and so you're going to have R steps, one step for each new vector you're finding for your new orthogonal basis formed from your original basis. And so this is V sub R, which is equal to U sub R minus the inner product of U sub R comma V1 over the norm of V1 squared, V1, minus the inner product of U sub R and V2 over the norm of V sub 2 squared, V2, minus dot dot dot, minus the norm of U sub R and Vn over the norm of Vn squared, Vn. VR. Everything's R here at the end, okay? R. Okay, so those first R steps, you've now formed your R new vectors for your new orthogonal basis. And so now at the end of these first R steps, again, you form the vectors V1 to VR in your new orthogonal basis. Okay? And so those are the first R steps. Okay, so you can stare at this. You'll probably want to look at this later. Pause the video later. I'm just going to add to this Gram-Schmidt process one optional step, and I'm going to erase this to write that optional step. But it won't really have to do with anything I wrote there. You won't have to refer to that. And so the last thing I want to say about the Gram-Schmidt process is there's an optional step after the rth step. So the optional step, this is after the rth step. Okay, so after the rth step, there's an optional step, and that is to convert the orthogonal basis to an orthonormal basis. Divide each vector by its length. In your orthogonal basis. Your orthogonal basis now has vectors in it. Take each of those vectors, divides by its length. All you're doing now is you're forming unit vectors in the same direction as those original vectors. Okay? The vectors in your new orthonormal basis will be in the same direction because you're just multiplying each vector by 1 over its length. You're just multiplying each vector by a number. And so you're not changing its direction. And if you're not changing the direction of every vector, they're going to stay orthogonal and perpendicular to each other. Okay? So dividing each vector by its length is multiplying each vector by a constant. And when you do that, you don't change its direction, you just change its length. You change it to length 1. And since all the new vectors have the same direction as all the old vectors, because all the old vectors were perpendicular, the new vectors are also perpendicular to each other. So this new set will have vectors with only length 1, because you're forming vectors with length 1 by dividing each vector by its length. So you'll get a set where every vector is length 1, and because the other set was already orthogonal, this new set will stay orthogonal, and now every vector will be length 1, and so now you'll have an orthonormal basis. Okay, and so that additional optional step after the R steps on the other board in the Gram-Schmidt process, adding this optional step will mean that in addition to transforming your original basis to an orthogonal basis, the optional step will go further, and you'll then take that orthogonal basis and convert it to an orthonormal basis. And so the Gram-Schmidt process with this optional step will convert any basis to an orthonormal basis. Okay? Okay, so really close to being done. Theorem 6.3.6. If W is a finite dimensional inner product space, then A, every orthogonal set of non-zero vectors in W can be enlarged to an orthonormal basis for W. Okay, so every orthogonal set of non-zero vectors in W can be enlarged to an orthonormal basis for W. And B, every orthonormal set in W can be enlarged to an orthonormal basis for W. So for every orthonormal set in W can be enlarged to an orthonormal basis for W. Okay, and so that's theorem 6.3. Okay, and that's the end of 6.3, and that's the end of chapter 6. Okay, and so next lesson we will start chapter 7 and 7.1. Okay, see you next time. Bye.